Hello. Today's topic is binary storage of sound files.
All right, so we'll move on to the next topic as well, which is very, very similar to the last one. That last thing that we've talked about has been very heavily focused on how do we calculate the size of pictures, but we're also going to need to discuss how do we calculate the size of audio files as well. So just like pictures, if we're dealing with audio files, we also have a bit depth. Although it's got a slightly different meaning, because remember that in pictures, our bit depth, that's not going to let me right off the side, that's annoying. So for pictures, our bit depth was how many pixels per, sorry, how many bits per pixel. And for audio, our bit depth is how many bits per sample. What is a sample? Well, if we're going to record, let's say that you're recording someone playing the piano, and for argument's sake, let's just say that they're only playing one note at a time, so a very simple melody they're playing on the piano. If you wanted to record that, then what you need to know at any given second is what note are they playing, or rather what's the frequency of the note that they're playing. And all we need to do is just say, okay, at the moment they're playing something that's 256 hertz, 256 hertz, 256 hertz, while they might be playing a middle C or whatever. And then when they change that note, then we're going to start recording differently. So the more often that we just take a sample, the more often we say, okay, at the moment, this is what the frequency that I'm hearing is, then the more accurate it will be. So usually we have a sample rate, which is down here, in hertz, which is how many samples per second, or kilohertz. So you might hear a really common one, for example, is 44,000 hertz, which means that essentially 44,000 times a second, we're finding out what is the frequency of the sound that I'm listening to right at this second. So the microphone is receiving constant noise, but it's not actually recording constant noise. It's just recording it in snapshots, of which there are 44,000 snapshots in a second. At a bit depth then is essentially how many bits are we using each snapshot. So we might be, all we're really recording is our frequency, which is some sort of floating point number. So we know that a floating point number could be using a 16-bit, something that looks like that, to store our sine bit and our exponent and our mantissa. So we know that we've got a way of recording its frequency. So if we're just storing a number that looks like that every 44,000 times a second, then we know that our bit depth is going to be, well, how many bits are we using for it? In this case, our bit depth is 16. And so we're going to be using 16 bits, 44,000 times a second. And so we just then have to multiply it by the duration. So for example, if we've got a 20-second audio clip that is using 8 bits and sampling every 4 kilohertz, then that's 4,000 times a second. We are storing 8 bits, and it's 20 seconds of audio. So I simply multiply 4,000 by 8 by 20, and that gives me this 80,000 bytes, which I can convert. So it's a very simple process. This one's much easier because we don't have to worry about color lookup tables or any other complex thing. You're nearly always just multiplying values together. But bear in mind that we've got sort of 3 different, at the moment, all our questions are just going to be on calculating file sizes. But in a test or an exam situation, and I think there's some sample questions later on here as well, in a test or an exam situation, it might obviously change the question up a little bit and have a different value as the unknown. So it might ask something like, we have a 20 meg file that is storing 24-bit audio at 96 kilohertz. What's the duration of the audio? So essentially, we've got file size is equal to our duration times bit depth times the sample rate. We could quite easily get a question that for which any one of those 4 different values are the unknown. To start with, we're just practicing where that's the thing we're trying to calculate, given that and that and that, but it wouldn't be hard to mix it up and say, okay, well, let's calculate that one given the other three, or vice versa.